All right, the next topic is one of the reasons why moment generating functions are so useful, especially when you combine them with the uniqueness theorem, because it gives us another tool for us to derive the distribution of a sum of random variables. And we can deduce what the distribution is by the uniqueness theorem if we know what its moment generating function is. So that's what we're talking about now, is the multiplication rule for moment generating functions, or for sums. For the moment generating function of sums of independent random. Okay. So what we're assuming now is that we're going to let x and y be independent and define S to be the sum x plus y. Then in this case, the moment generating function of the sum, by definition, is the expectation of e to the t s. S is x plus y, e to the t x, e to the t y. But now x and y are independent, so we can write e to the tx expectation e to the ty. So it's the product because x and y are independent, right? And now this is the moment generating function of x times the moment generating function of y. And if we consider the cumulate generating function, well, that's the log of the the log of the moment generating function. But the moment generating function, as we just saw, is the product. And the log of a product is the sum of the logs. And each of the logs itself is the log of a moment generating function. So the cumulant of a sum is the sum of the cumulants, sum of independent random variables, sum of the cumulants. Okay, so let's see how we can apply this. If x, let's do example number 1. Let's let x be Poisson with parameter lambda, y is Poisson with parameter mu, and let's assume that x is independent of y, right? Well, then by what we just said above, the moment generating function of S is the product of the individual moment generating functions. We already calculated up above the moment generating function of the Poisson, right? E to the minus lambda plus lambda e to the t. So that's for x, and e to the minus mu plus mu e to the t for y. But those combine now for e to the minus lambda plus mu plus lambda plus mu e to the t, which is the moment generating function of Poisson lambda plus mu. And we can conclude that S is Poisson lambda plus mu precisely because this is finite in a region of 0 for t. And so we have the uniqueness there. Another application is if we have gamma r lambda y is gamma s lambda, and again x independent of y, then the moment generating function of x plus y is the product of the moment generating functions. We've already computed the moment generating function of both of these. They are lambda over lambda minus t to the r, lambda over lambda minus t to the s, which come together to be lambda over lambda minus t to the r plus s, which tells us that s is gamma r plus s m rate lambda. Again, by the uniqueness theorem, because we can show that this is finite in a region of 0. And then finally, let's have independent normal random variables, one with mean mu sigma squared, one with mean nu and variance tau squared. Then again, it's the moment generating function of x times the moment generating function of y. Well, what do we get from this? Well, the means add up and the variances add up. So x plus y, this is exactly the moment generating function of a normal with mean mu plus nu variance sigma squared plus tau squared. So, and this of course extends to more than two. So if we have multiple, if we're adding up multiple independent random variables, the moment generating function of the sum is the product of the moment generating functions. And leveraging that with uniqueness, this would have given us yet another way to derive the distributions of sums of independent Poisson, gamma, and normal, which we've already derived earlier in the course.